All right, so the homework is just finishing the examples that were in the notes packet. For these first four questions, it says match the logistic equation with its graph above. So one thing about all of these equations is that they all have a carrying capacity or a horizontal asymptote at 12. So that's not going to help me distinguish between the graphs. Usually for any function, the easiest thing to do is if they have different y-intercepts, try to match those up. So I can kind of mark off where I think the y-intercepts are for these. And because they all seem to be in different places, except maybe A and B look to both be, let's see, every tick mark here is marked as 2. So it looks like that's at 6. This one might also be at 6. This one looks like it's at 2 or maybe 3. And this is 2, 4, 6. This one might be 8. So I'm going to see if these are close or if these are what I get when I plug in 0 here. So y-intercepts are usually easy to find because you plug in 0 for x. So if x is 0, I get 12 over 1 plus e to the 0. 12 over 2 is 6. Okay, so this is one of these. And then this one, if I plug in 0, I get 12 over 1 plus 1 half. That's 12 times 2/3. 12 over 3 is 4. 4 times 2 is 8. Okay, so we said D was 8, and I didn't see any others that were 8, so 2 is probably D. For this one, if I do 0, I get 12 over 1 plus 3, so that's 3. That would be this one, right? I said I wasn't sure if it was going through 2 or 3, so okay, that's going through 3. So this is C. And this one, if I plug in 0, I get 12 over 1 plus 1 again. So how do you know the difference between which one is A and which one is B? If I look at the two graphs, B looks like it's gone through a horizontal shrink because the slope is like more steep, or these points are kind of scrunched together horizontally, for lack of a better term. And remember back to your transformations days of Algebra 2 and pre-calc, the only difference between the two equations is whether it's e to the negative x versus e to the negative 2x. And remember, if you are inserting a number larger than 1 in absolute value into the function, like this is like f of 2x basically, that is a horizontal shrink. So 4 has to be B because it's gone through the horizontal shrink. A is not quite as scrunched in here, so that's got to be number 1. All right, number 5 says the logistic equation, so we're told this is logistic, models the growth of a population. So here's our logistic equation. Find the value of K, find the carrying capacity, find the initial population, determine when the population will reach 50% of its carrying capacity. So the first two answers we should be picking out of the equation. Remember, this is an equation that you need to have memorized. In general, this equation is carrying capacity L over 1 plus C e to the negative KT. So I can see that K it's not negative 0.75. The formula is negative KT. So K is just positive 0.75. The carrying capacity is L, and I can see that's the numerator here, 2,100. I don't think we have any context to this problem, so no labels. What's the initial population? So that would be plugging in 0 for time. And it's not just, like, that's not equivalent to C, right? C is 29, but that's not the initial population. If we plug in 0, we get 2,100 over 1 plus 29 times e to the 0, which is just 2,100 divided by 30, 1 plus 29. And let's see, what is that? 70. So 70 was the initial population. Determine when, which is T, the population will reach 50% of its carrying capacity. So that happens at a point of inflection, but I don't want to overcomplicate things. When will we reach 50% of carrying capacity? So this is just saying, like, set P of T equal to half of, so set P of T equal to half of L. So when is P of T equal to, let's see, half of 2,000 is 1,000, half of 100 is 50, so 1,050. I can check that on a calculator too. This would be a calculator problem. So solve for T. I'm just going to use Desmos. I could go through the algebra of setting this equal to 1,050 and multiplying things around and natural logging and whatnot. But if we're going to use a calculator anyway to get a decimal approximation, then I'm just going to use Desmos. We do have the skills to solve for this algebraically and keep our answer in terms of natural logs, but I don't think that that's necessary. So let me look at what I'm solving here. Okay, so one line is just y equals 1,050. And the other line is my equation, which I need to, there we go, this equation right here. So P of T is equal to 2,100 divided by 1 plus 29 e to the negative 0.75. Now, this is annoying, but, oh, no, wait, it worked. What? If I'm trying to plug numbers in up here, like multiplication, I was about to say this is annoying. The T keeps dropping down, but I guess that's only if I'm trying to type in. If I were trying to type in like times 5, yeah, that's the annoying thing that keeps dropping down. So anyway, whatever, just type that. That was okay. I can see P of T. I can't see this Y because it's at 1,000 and my window is definitely not scaled. So I am zooming on out here. You can also go into settings and adjust what your Y values are going to be, but it's not too hard to zoom out in Desmos. Click near the point of intersection. You should see a gray point, which solves for T. So get back to where my answer can be written down. Okay, so T is approximately 4.48. Oh no, this is going to round up. 489. It rounds up to 490. And I don't know if this is yours, so I'm just going to leave it like that. All right, and then the next part says, write a logistic differential equation that has the solution P of T. So this is just testing, have you memorized this dP dt formula yet? So I know we just did the notes, so maybe not, but here it is, dP dt. The setup for this in general without numbers plugged in is K times P times 1 minus P divided by L. So all we need to do is plug in the K and the L value, and they match the K and the L in the logistic population growth model. So for this problem, dP dt is equal to 0.75 times P times 1 minus P divided by 2,100. And that's it. I could give my initial condition too. I don't know if I need to do that, but P of 0 equals 70. I could say that as well. All right, number 6, the logistic differential equation models the growth rate of a population. So we're told this is logistic. So that means we know that we have K right there and we have L right there. So find the value of K. K is 3. Find the carrying capacity. That's L. That's 100. Determine the value of P at which the population growth is the greatest. So this is different than the previous question where this part D, it said determine when the population will reach 50%. That was asking me to find lowercase t. This is just asking me to find P. So dP dt, the population growth rate, is greatest. In a logistic differential equation, it's always greatest at 1/2 of carrying capacity. So the value of P is equal to half of 100, 50. So we don't have to bother finding P. And actually, I don't think we can find P because we don't have any initial conditions. So we don't have to go through and set P equal to anything. They just want the value of P. All right, number 7, find the logistic equation that satisfies the initial condition. So if we're told to find a logistic equation, that means that these are logistic differential equations. And I also know that because these are outputs. If these variables said t on this side, they couldn't be logistic. All right, so how do I do that? Well, I pick out some stuff that I know. Like there's a 1 in front of this y, so k is 1. This is the L, the carrying capacity is 36. And we have this initial condition because remember, in general, the formula for a logistic growth equation is P equals L over 1 plus C e to the negative KT. I know L and I know K, but I don't know C. So that's what this initial condition is for. All right. So, and the initial C is not just 4. So you do have to do some math here. All right. So let's see. So P is 4 when we have 36 for L over 1 plus C times e to the 0. So if I multiply 1 plus C over to this side, and then I divide 4 over to this side, I get 1 plus C equals 9. So C equals 8. All right, so find the logistic equation. So P equals, L was 36 over 1 plus 8 times e to the negative. K is 1, so you can write 1 if you want, or I'm just going to write negative t. Negative 1 times t, negative t. All right, now this one is not in the proper form for a logistic differential equation, so I do need to get it into its factored form. The way I know it's not in the right form is because it has to be something times parentheses 1 minus P over L. So I need to do a bit of factoring here. I need this to be 1, so I have to factor out 4y over 5. And I'm going to do this math off to the side here. So y squared over 150. If you are factoring out 4/5 y, you're really dividing by 4/5 y, or you're multiplying by 5 over 4y. Okay, so I don't want to do 4 times 150. Do 5 divided by 150. That's 1 over 30. So there's a y left in the numerator, and we have 30 times 4, 120 down here. So this is the dy dt. I want it to be in this format because I don't want to mistakenly say the carrying capacity is 150. It's actually only 120. So K is 4/5. L is 120. I'm going to use the initial condition set up with my formula to find C. So P is equal to L over 1 plus C e to the negative 4/5 t, and plug in my initial condition. So 8 is equal to 120 over 1 plus C e to the 0. So same steps I did before. Let's multiply 1 plus C over here. Do 120 divided by 8. So let's see, 8 goes into 12 once. You're left with 4. 8 goes into 40 5 times. So C is 14. And P is equal to 120 over 1 plus 14 e to the negative 4/5 t. All right, number 8. A conservation organization releases 25 Florida panthers into a game preserve. After 2 years, there are 39 panthers in the preserve. So let's write down those two ordered pairs. Initially, time 0, we have 25 panthers. 2 years later, we have 39. The Florida Preserve has a carrying capacity of 200. L is 200. Write a logistic equation that models the population of panthers in the preserve. So, in general, P is equal to L divided by 1 plus C e to the negative KT. Always plug in that initial condition so you can figure out C, because you can't find K if you don't have C. So 25 equals 200 over 1 plus C e to the 0. 1 plus C equals 200 over 25, which is 8. So C is 7. And then let's plug in the other condition. So P is 39. That's equal to 200 over 1 plus, now I know C is 7, e to the negative 2 goes in for T, so negative 2K. Now again, we are going to be using a calculator to find our answer. So I can, even though I could multiply this denominator over here, isolate the e, natural log both sides, get a nice exact answer, I can also just use the unrounded decimal value for k. So I'm going to switch to Desmos here. If you're allowed to use a calculator on an AP problem like this, then this is the whole like work smarter, not harder idea. You do not want to spend a bunch of time solving an equation algebraically if you're allowed to solve it graphically. So I'm just going to say y equals. So I am just graphing y equals 39 and y equals 200 over 1 plus 7 e to the negative 2k. And my window was zoomed out from whatever my last problem was. We're only at y equals 39, so I do not need to be way up here at 1000. So yeah, here's this. So clicking near the point of intersection. This other point is just where we have a y-intercept, it looks like, so we don't need that. So make sure you're on this one. And this is just k. You do have to give the full version of k, so do not round it, because if you're going to use this to, the only bad thing about solving by graphing is if you're going to use this to calculate further answers, then you need to make sure that you haven't rounded something to then use an answer to then find an answer, because your answer will be thrown off. Okay, so that's k. And this was just write the formula. So P is equal to 200 over 1 plus 7 e to the negative k, which is this whole decimal, times t. Now, I understand that this is a rounded version of k, but we just don't want to round what they're giving me from the calculator, basically. If you're worried about that, then of course you can do all of your algebra, do all of this stuff, swing this over here, divide this over here. You should end up with negative 2k equals ln of 200 over 39, subtract 1, divide by 7, divide that by negative 2. I mean, that's the exact value for k, but we can go ahead and give the full decimal that we got off of Desmos, and that's acceptable too. Okay, find the population after 5 years. So this is just find P of 5. So I do need to make some adjustments to what I have typed into Desmos. So I don't quite have the full P equation on here. I need to erase what I have in my exponent. So negative is still in there, 0.26403. And then this is what I was saying. Like I want to, if I hit times 5, it's going to keep doing that. I can do that in parentheses, or I can just use parentheses to show my multiplication here, or parentheses around the whole thing. So 69.695. But remember, we're talking about animals here, so let's call that about 70 panthers after 5 years. All right. When will the population reach 100? So this is just kind of what we did in a previous problem. Set P of t equal to 100. Now I have P of t right here, except I have 5 plugged into it. So erase that 5 and put a t back in. So here's this. And then let's get that off of there. And we want to know when is this equal to 100. So type in y equals 100, and it's right there. So 7.370. This is when time is about 7.370. Time is measured in years. Okay, let's see what the next question is. At what time is the panther population growing most rapidly? So this is asking you about dp/dt. dp/dt is greatest, most rapid growth, at 1/2 carrying capacity, which is half of 200, so 100. And we just answered that. P of t equals 100 when t is about equal to 7.370 years. If this were a different number, I would just change out my y equals in Desmos and see where they intersect. All right, so hopefully this helps you kind of understand how you're working with the two models. Definitely memorize the setup for logistic growth and the setup for the, I guess it's right here, for a logistic differential equation and how the two are related. It makes these problems a lot easier.